Dear participants, sir is joining very soon. Actually, there was a little bit confusion about the timing of the program. Yesterday, his session started. That means first session started at 6:30. So sir was in that opinion like today also it is 6:30. But I informed him he is going to join very soon within a few minutes. So please be there, stay connected. Attendance today is quite less. It is seen from here. Um, and if you are not maintaining your attendance, we cannot help you from our side. So please maintain your attendance. Once again, I am requesting to all the participants in the general group as well as here. Otherwise, once your attendance is falling below the criteria of the AICT, it 80% is the criteria. That means out of 10 sessions, you have to attend minimum 8 sessions. And there is 13 session, you can calculate 80% of 13 session. So please be maintain your attendance, and you can tell your friends also who is in close contacts with you people. Please add me. Sir has joined, I think so. Now we will make him as a presenter. PK sir.
हाँ बोलो.
Yeah. Just I'm making Madhusudan sir as a presenter. Then everything will be accessed to him. Yes, sir. Professor Madhusudan sir.
Hello.
Yeah. Now you are in here, sir. And dear participants, our expert for first session today, Professor Madhusudan Singh sir, will continue the session where he left yesterday. And there is no need to introduce him once again because you are well aware from sir. Yesterday, sir has given a very nice presentation and wonderful discussion with you all. And today you will have more time to discuss with sir. You can ask your queries in the chat box. I will keep the questions in front of sir. And yeah, sir, now you can start, please. Hello.
Hello.
Yes, sir.
You can say. Can we start now?
Yes, sir. You can share your slides.
अच्छा, ठीक है. Thank you.
Yeah.
Hope these slides are visible.
Yes, sir.
Slides दिख रही हैं?
हाँ जी. यहीं से यहाँ से बाकी था. यस. हाँ यस, इसके पहले से था. इसके पहले वाला SRF थियरी से बाकी था, आई थिंक सो.
हाँ ठीक है. So this is, I hope, what we discussed yesterday.
Yes.
Design of single phase wind energy conversion system using squirrel cage induction generator. So I hope this design we discussed yesterday, the design of all these 6 components of a WCSC, wind energy conversion systems. And before that, we had also discussed arrangement for 3-phase wind energy conversion system. The only change you see here is that you have a 3-phase machine acting as a induction generator, which is driven by wind turbine. And since it is a 3-phase squirrel cage machine, you need a 3-phase capacitor bank for its 6 citations. In single phase, you had added a single capacitor in auxiliary winding. And obviously 3-phase load and a VSC also of 3-phase nature using 6 switches and battery. So today my focus will be more on how to operate these VSC. What are different control schemes through which we can control these VSC so that we are able to maintain the voltage and frequency in the microgrid if it is a wind-driven system and it is using a squirrel cage machines. So if I talk about a few conventional methods which are used to control the VSC, one of the method is SRF theory, synchronous reference frame theory, which is used for operating this VSC. So this is just a diagram shown for single line diagram, but it could be for a 3-phase systems as well. So the control scheme, if you see here, is basically for 3-phase. And you can think of how this scheme works, as its name indicates, synchronous reference frame theory. Here you have inputs like the load current of the nonlinear or linear loads. So the load current is sensed, and also the supply voltage, the generator voltage, is sensed through voltage sensors, through current sensors. And then we use transformation. Hope you are aware of 3-phase to 2-phase transformation. We also called ABC to DQ transformation techniques. So using this transformation, we can get a DC component of the load current, which is responsible for generating real power in the load. And for transformation, when you convert ABC quantity of current into corresponding D and Q component of current, so a 3-phase to 2-phase transformation, you need sine cosine angles. So for that, we take help of PLL. So you have a phase lock loop which takes the input supply voltage and generates cosine and sine theta. These sine cosine thetas are used in this transformation matrix. So these all are done by the device, the controller which we select, if it is a DSP based controller or maybe your DSP based controller using either D space, or it could be the another version of the same, which we called micro lab box. So using those two, you can implement this. And finally, the source current of the generator also sensed, and the reference current which we generate for the systems are compared through a hysteresis current controller. So these controllers generates a switching signals for the 3-phase VSC, which is responsible for ensuring the kind of control we want to implement, whether we want to supplement reactive power, we want to supplement both real reactive. At the same time, this 3-phase capacitor, 3-phase VSI DC link also need to be maintained. So for that, you have a separate PI controller which take care of the DC link voltage is maintained with this PI controller. This is for maintaining the magnitude of AC side voltage. So as you have seen here in a 3-phase generation, you need to maintain the magnitude of voltage as well, AC side, and DC side. This DC link also need to be maintained if you want to ensure here a PWM control. So usually this DC side kept higher than the peak of this AC side. So for controlling this DC link voltage, maintaining the DC link voltage, we use a separate PI controller which requires for discharging this battery, and or if there is a capacitor, that also need to be, voltage of that capacitor also need to be maintained. And at the same time, the AC terminal voltage, because this is a standalone system, if you change the load, there is a possibility the voltage of the terminal may falls if there is no excitation system which can provide variable reactive power. So this VSC, in fact, we are using to supplement the reactive power requirement of these generators. And also, if the generator capacity is less, this battery system can support the load. So the two things this VSI need to ensure is the reactive power support for SCIG, as well as the real power support, because we are using a battery bank here. So to ensure these two requirements, what you need to do is you need to have a regulator for voltage and a AC side voltage, a regulator for this DC link voltage, apart from uh, detecting the current component which is responsible for transfer of real power. So this is what is being done in this SRF theory. If you see this AC side, this bottom block is sensing the peak of the AC side voltage, comparing with the reference peak, and this PI controller ensure that adequate reactive power, that is IQ component of the two-phase current, is modified to ensure that reactive power. And similarly, if you see here, the DC link is also compared, and the real power component of the load, that is IDC, is added with this. So this is the net real power current responsible for real power uh, transfer, as well as the loss which need to be maintained uh, uh, to ensure the DC link voltage constant. So this loss, usually we understand the losses in the switching devices, and also if the battery bank is there, internal resistance loss. To cover those losses, these VSI need to draw some real power from the source. So this is how it maintains the DC link. So I hope this is clear. The two component of current, one responsible for real power transfer, other responsible for reactive power transfer, need to be clearly distinguished. And finally, these two-phase current again need to be transformed to corresponding three-phase reference current. And this three-phase reference and these actual three-phase source current will now compare to operate a hysteresis current controller. So here is a three-phase hysteresis current controller, which will finally generate 6 PWM signals for that VSC. So this is all about the technique, what is known as SRF technique, a very conventional technique, relatively easy. But what you need to hear is you need a low pass filter here, because this side is all DC quantity, this side AC. So with this transformation in synchronous reference frame, we get a equivalent DC. So this low pass filter ensure that the only DC component of the real power is being extracted. So this technique is also being used to operate the VSI, and these are the few results. If you see here, shown for source voltage, which in spite of load current, you see initially only one phase of the load current is shown here. The load current is increased, decreased, the supply voltage remain intact. It means the generator is able to supply the adequate reactive power. So this is the current which is supplied by the this is the current which is supplied by the generator. So if the load current increases, the corresponding source current increases, and the DC link is maintained. So this is just to show you some results with this SRF technique, and this is another technique which you see implement instantaneous reactive power theory. So I hope you know that in this three-phase system, if we can sense the three-phase AC voltages, we can sense the three-phase AC load current. Then using this three-phase to two-phase transformation, we can get their corresponding alpha component of voltage, beta component of voltage, and these are the standard equation which give you the instantaneous real power and reactive power, which after filtering you have a net real power in watts DC, average real power you can say. So the low pass filter simply get the average of this real power, average of. So this you see that here we directly calculate the real power and reactive power references. That's why you call it as a instantaneous reactive power theory. Here do also we need a similar kind of arrangement for maintaining DC link voltage. So you need to sense the actual DC voltage with the and compare reference PI controller. So this will be added to real power, and similarly for AC side voltage also you need to sense the peak of AC side, compare with the desired peak, and then this controller will create appropriate component of the reactive power, which will be get added in the reactive power demands. And they see this is the reference of real power and reactive power, which finally we convert into the current using this transformation. And again, you can apply an inverse Clark to get a corresponding three-phase AC reference current. Actual AC line current you can, source line current you can sense, and again you can have a hysteresis current controller here which can compare and generate the adequate switching signals for things. So you see here, in spite of handling in terms of the real and reactive power current component, we are directly calculating the real and reactive power. That's why you call reactive power theory. Results are quite interesting here. You see, we have a generator voltage, source voltage Vs, source current. This is the current which is supplied by VSC, and this is the load current. So load is a nonlinear load. That's why a square wave load current. And you see, if the load is demanding something which is square, a generator which is supposed to provide a sine, if you directly operate this load, this current will get distorted. So in presence of this VSC, you see that whatever is the difference between this sine and square is being supplied by the compensator or VSC. So this is a VSC current. You see, if you add this VSC and this is square, this will come sine. So in other words, you can say that this controller, this VSC, is trying to compensate what is missing in the load current, which is what is missing in the source current to make it a sine current. So this way we are able to maintain a pure sine current from the generator. You are able to maintain the quality of voltage and current in the generator. At the same time, you see, whatever the load changes we are making here, the DC link is remain maintained. It means the DC PI controller which we have placed on. So this technique also effectively implemented for this kind of control. Other possibility is power balance theory, almost in the similar line. So I may skip it because you see more or less same blocks. The only thing is here something different is sense, and something what is desired is changed accordingly. Now, recently we have noticed many new modifications of these methods using adaptive theory-based control algorithms. And I think this is an area where Dr. Asutosh has worked a lot. He has used many of these techniques for improved performance of VSCs, especially for standalone operations. So one or two of these techniques are also shown here. We'll just try to see that what are their mathematical background and also how they are implemented using MATLAB, some simulation result, and I think some hardware work also being presented by Dr. Asutosh in this matter. So just have a look, mathematical modeling of line control algorithm. So I hope these are the some background of adaptive control methods. What we mean exactly by adaptive controls. Uh, Without adoption, how you find an error signal. With adoptions, how we modify the errors again and again till we get an optimum values. So based on these general theory of adoptions, the techniques are being utilized, especially for operation of VSC, where you see here we are using PLL again to sense, the AC side voltage and find out the frequency, because here we are trying to maintain voltage and frequency of this standalone system both. As usual, DC link voltage also you need to sense, compare with the actual, and again that error will process through a PI controller. As far as calculating the component of this real and reactive power component of current are concerned, for that we are using these adaptive mechanisms, iterative mechanisms. And you see here, what we are doing is the three-phase terminal voltage generator we are sensing through voltage sensors. And we are trying to compute the in-phase component of reference current and quadrature component of reference current. So how do you do that? Say you have a AC side sine voltage like Vm sine omega t, Vm sine omega t minus 120, minus 240. So if you just divide these voltages by their peak value, you get their template sine omega t minus 120 and so on. And if you so that component, sine template is basically the in-phase component, and a component which is just 90 degree out of phase with this will be obviously called a quadrature component. So it's just like that. Here you got something sine. Here we are expecting cosine. So 90 degree phase difference. And like that, since we have to maintain the AC side terminal voltage, we are trying to get the peak of the AC. So this just mathematics. I hope you can understand general three-phase in a three-phase AC system. If all three-phase instantaneous voltages are known, like Vm sine omega t minus 120, 240, we can derive the Vm by simply squaring, then dividing by √3. So this is a mathematical way to get the peak of the supply. So this is the actual value of peak is compared with what we want, and this is processed by a voltage controller, what you call PI controller. Output of PI controller is added to the weightage which we get for reactive power components of the through quadrature component. And similarly, the real power component you add in the real current which we derive through this adaptive mechanism. So what is the modification? If you see with the previous technique is mainly these rectangular blocks which implement the adaptive mechanism in finding the most appropriate weightage for this real and reactive component of the current. The rest of thing, if you see logically, more or less similar what we discussed. But these mechanisms are superior in respect of previous technique because they are able to address the uncertainties, especially involved in the operation of especially the wind-based generation system, because you know that wind velocity or wind is such a parameter which has a lot of intermittency. So to counter those intermittency, these adaptive techniques are more appropriate according to the situations. So those who are interested for more detail, they may see our papers on these topics, and the rest of thing is just comparison and finally generation of PWM signal to the VSC. This LMS is being used for control and V by F of a distributed generation system. So a similar block diagram here. So this is the schematic diagram of the system where these two algorithms are being tested. If you see, it's simply a wind generator driving the rotor of a three-phase induction machine. So this is your generator part of this wind energy conversion system. And since it's a squirrel cage machine, the voltage generated from stator side with help of a capacitor bank having appropriate capacitor value, and you have a neutral point here available, so that way you have a facility to drive a three-phase 4 wires system, in fact, where you can connect all three-phase load as well as single-phase load. So this neutral point is available, and that's enable you to connect three single-phase diode rectifier-based load. You can call a nonlinear load. Why three single-phase? Reason simple. If you want to create the effect of single phasing, that if one phase goes out, only two phases are there. Even in those worst case situations, whether your controller is able to maintain the terminal voltage of this generator or not will be ensured if you have this kind of load available. So the facility shown here, in fact, through these switches is mainly for creating, say, one phase goes out, the switch 1 open, switch 2 open, only one phase is there. It's even under this worst situation, when only single phase load is there, the two phases are out of operation, you will see that the generator side current remain balanced, and also the profile of the current remains sinusoidal. That's the beauty of this converter. And even if we see the quality of this current have very less THD, it means it's very close to sine. So that way you find that these two algorithms which we had stated, LMS algorithm, adaptive control algorithms, are more effective in reducing the THD of the current and also making the overall quality of the current and voltage profile very close to sine. So this is something about this schematic diagram. And since in this circuit we want to support the load with real power also, we have used a battery bank at the DC link you see, and now the rating of the machines are also shown here, just to tell you that for simulation purpose, experimental purpose, we have used a machine, a generator of around 3.8 kilowatt, and wind speed is being considered 12 meters per second. The rotational speed per unit, pitch angle, etc. These are the parameters which are being used for simulation of this wind turbine. And well, so hope you are able to see all these slides. These are the generator side rating. If you look, rated power of the generator 3.7 kilowatt, just 5 HP machine. And this is a machine which is especially designed for a low voltage, 240 volt line to line, you see. Frequency 50 Hz, 4 poles, and these are the parameter of these induction machines which is used for conversion of this wind energy into electrical energy. And these are some initial conditions to characterize the magnetization characteristics of this generator. Simulation data for transformer and load also given. The transformer which we have considered is 2.4 VA and frequency 50 Hz, primary side 140 volt, because AC side we are keeping low because just for experimental purpose, because if you have AC side higher, DC also you need to modify, and the inverter rating, etc., device rating will go up. So in view of that, a nominal just rating is selected just to validate the simulation results through experimentals. These are just MATLAB block. You see how this scheme is being implemented. Power circuit, especially the transformer part, VSC part, the battery energy storage system along with the battery, and the control blocks are shown in a sub block like this, which will be further extended later. And these are the few measurements on the turbine and generator. And these are the single phase loads, what is modeled using a single phase rectifiers, diode bridge rectifiers. DC side you have a combination of R and L. So that AC side current will be, if the inductor is high, the AC side current will be almost a square wave having a lot of harmonics. And just to demonstrate that the technique able to eliminate all these harmonics from the source current is one of the idea to select this rectifier. These are the control technique which are being implemented in the MATLAB using the equations which were shown here, if you see in the beginning. So all these equations what we have shown are being implemented as it is in this control block diagrams. And finally, you see that the PWM signal, which is created by comparing the reference current, three-phase reference current with the actual ABC currents, produces the 6 pulses simultaneously to all to 6 pulses, which can be applied to the VSC of the systems. Now you see here some of the results of these control techniques are also shown. The very first one is the load current. You see, we have used 3 rectifiers. So the AC side of these rectifiers are drawing the non-sinusoidal current, just like a square current. But since we have shown all 3 currents, so they are just imposed on each other. You will see that these are the square wave and also displaced from each other by 120 degree, because their corresponding AC side voltage is displaced from each other 120 degree. So with this load current, you see the This is the profile of in-phase component of voltage template, what we have called UPA. So in-phase component is pure sine, and similarly the weighting factor, the weightage which were calculated using this adoption mechanism, you see continuously varying for all the phases, A phase, B phase, and these are the real power component which are being estimated using this weightage. Terminal voltage, the frequency of the generator you see here more or less constant, and this real power component of power. So all these control signals, this is basically intermediate signals of the machine of this scheme is shown, and generator current, if you see, is almost sinusoidal currents. So you see that this particular adaptive control algorithms are more effective in operating such standalone schemes, ensuring good quality power supply, not only in terms of voltage profile, but also frequency. And these are the few waveforms of the power circuits you see. You have ABC voltage, so the generator terminal voltage intact in spite of changes in the load current you see. So even the load current we are able to change. You see that profile of voltage is maintained. Compensator current also shown here, and that VSC output current, terminal voltage, and that peak of the terminal voltage also shown. Frequency is, you see, almost constant, 50 Hz. And apart from that, since you have a neutral point, so neutral current is also shown. Whenever there is an unbalance, there will be some current going to the neutral. So you see here, when there is an unbalancing, one of the phase goes out, the neutral current you see available there. So to ensure that the AC side generator current remain balanced. So this is the battery discharging profile also shown. The DC link you see well maintained. So these are the few interesting results of this particular schemes when the DG system is operating with variable linear loads. These are few energy balance of the power balance equation. Power balance profiles are also shown here. You see that includes the generator power, the load power, and the battery power. So you see the generator operates almost at a fixed power. So this is how it ensures that frequency remains same of the generator. If there is a variation in the load power, you see it is being pop-up with the battery. So the generator is operating at its full rated power, and that's why the frequency remains 50 Hz. If there is any change further in the load, either exceeding the rated power, it is made by the battery. So you see the battery power here. You see that the total load power is this. So you see here, this is the load power requirement, and this is the generated power. So obviously generated power is more than load power. So the remaining, this balance is used to charge the battery. And at this moment, you see when the load power exceeding the rated power of the generator, then this battery is supporting the load. So you see that the load power, the battery power is now positive. So battery along with the generator both able to meet the load. So this is the profile of your power balance, how the power is maintained, and hence the frequency is maintained in this system. Battery charging, discharging currents also shown here, and battery profile voltage. So the deviation of battery voltage you see is not much. It's just 320 to 320, just 2-3 volt deviations. This is the enlarged version of the waveform shown, just to ensure that even the load change occurs, the DC link is well maintained. So this is just the nature of power balance in this microgrid, which is supported with a wind-based generation. And these are the few THD profiles of voltage and current. Source current waveform you see is almost sinusoidal. THD very less, around 4%. So the VSC is able to ensure a almost sinusoidal current from the generator, though you have a load current you see which is demanding a highly distorted current, a square current which has a lot of harmonics. You see this harmonic is of order of 30.55. So the load which is demanding such a high harmonics, the source you see is supplying only a limited harmonics, 4%. The rest of the harmonic compensation is being done by your compensator, that VSC. So this is how the harmonic spectrum of this microgrid on the load side, source side is maintained. Now, this is a laboratory setup what Professor Asutosh has also developed, and you see you have inductors. These are the interfacing inductors. You have machine here, motor generator set, and for in the laboratory, since we can't develop a turbine system, so we use even our simple DC motors, AC motors as a prime movers. So usually we run those prime movers with the help of drives, and we have a capacitor bank here, and then these are the loads and other arrangements. These are control arrangements, inverter, VSC, etc. So just to show you the setup through which these results are found. And these are the individual unit VSC. That is a 3-phase VSC inverter, and hopefully this is a semicron ready-made inverters which is being used for this purpose. This is your D space machine setup and all. These are the sensor circuits. You can see the current sensors and the voltage sensors which are used for sensing the respective currents and voltages, 3-phase systems. And to operate this sensor, you need their power supply. So this is a power supply unit. These are the isolators circuit. Hope you know this IC, very popular and commonly used IC for opto isolators, which are used in the driver circuit. I mean, the signals which comes from your D space are not directly applied to inverters, but an isolation is desired. So you have 6 signals, so 6 such parallel arrangement is made, what is known as a driver. So driver is nothing but is electronic circuit which not simply converts a low 5 volt here to a 15 volt, which is required to run the IGBT, but also it has its all separate ground. You see this side ground is different, this side is no common ground. So that 2 sides grounds are independent through this isolation mechanism opto isolation. So this IC is dedicatedly used for this purpose. Whenever you want electrical isolations, that is electrical isolation between the control circuit and power circuit, because inverter switches are power circuit, and the control signals which you are generating through your MATLAB and the space, they are all control circuits, so need to be isolated. This is a common isolation circuit. And you have 6 such pulses, you need to duplicate the same circuit 6 times. So mostly this circuit is used for your diver. This is just to show you some of these circuits. And here is a deadband circuit, because whenever you have the 2 switches in the same leg, one upper, one lower, and you want to operate them, you have to ensure that once one switch goes off, then only the next switch goes on. If there is any overlapping time, you will see it will create a dead short circuit against the supply. So to ensure that, we provide a dead band between the 2 switches, and this circuit ensures that dead band. But for some times, none of them are on. So these are just few waveforms related to ensure a dead band of around 2.5 microsecond between the switching of 2 switches. So this 2.5 microsecond, if you compare with respect to one cycle of supply, which is 50 Hertz, 50 Hertz one cycle, you understand 20 millisecond. With respect to 20 millisecond, is 2.5 microsecond is very small, and even can't be easily noticed when the switching happens. But yes, this is sufficient to ensure that there is no dead short circuit in the system. These are the internal circuits which are there to ensure the falling edge, rising edge, and that ensuring dead band. Now these are the details of all the components which are being used in this experimental setup. We have used a induction machine of 7.5 kilowatt, 440 volt. Prime mover is a 5 HP machine, again induction machine, and generator. You see the AC drive is 7.5 kilowatt. The prime mover and generator are of the same size. The capacitor bank is a 3-phase capacitor bank and requires a capacity of around 4200 var. Or LEM make sensors are used for current and voltages. Interfacing inductor used are 16 millihenry. That is the inductor which is connected between the VSC and the generator terminal. And the capacity of the VSC, or the converter, Semicron make, itself is a DC link maximum up to 1200 volt. Though in this experiment it is not fully utilized, we are operating at a very low level. But yes, that capacity is as high as 1200. BSCS, that is battery storage, used is around 7.5 ampere hour. So there are 12 volt batteries to ensure total of 432 volt. This is the processor detail used in that microlab box or DSP and the D space. And deadband IC is this one, opto isolator, as I said earlier, 6N136. So these are the specifications and rating of the various devices, machines, sensor, etc. And these are few experimental results just to validate the simulation. What I showed you in the beginning, you see in the control signals, all those control signals which were shown. You have a in-phase template, a pure sine template, the load current, which was a square wave. These are the real waveforms which are captured through a 4 channel DSO. and the loading requirement is changed from time to time. See, at this moment, the load is switched on. Here, the load is switched off, and you see under all these situations, you see that your template doesn't modify, template remain intact, and the weightage, etc., the weight calculations value situation changes according to the load. So you can understand if the loading situation is changing, the weightage of the parameters are modified, and accordingly the real and reactive component of currents are modified, and real power, reactive power is modified in the system. These are the AC side voltage of machines. You see the supply voltage or the generator voltage. Generator phase A current, you see the both voltages remain sine, and though the load current you see here is square wave, the source current is a pure sinusoidal current. And how do you maintain this pure sinusoidal current? Well, this one is demanding a distorted current. You are feeding what is required to ensure sine here through your compensator. So you see this is the compensator current, which is just the missing component of the square, which ensure a sine. So, and you see the load current is removed at this moment, the corresponding the controller current is increased to compensate so that the generator current remain sine. So these are the few experimental results just to validate the outcome of these algorithms. BSCS parameters are also shown here on the battery voltage, battery charging current, as the load is changing. So you see when the load is increased, the battery charging has come down. When the load was switched off, that current power was used to charge the battery. So this is how the scheme works, and finally it demonstrates the effectiveness of this algorithm in operating this microgrid arrangement. I think there are many similar results just for your knowledge, but those who may be interested, these are also, you see, the power balance profiles of your actual systems, where you can see the power of the generator, the load, and power of generator, this blue color you see, remain intact, fixed. Though the load power is changing, the battery is accordingly adjusting the excess power or deficit power. So this is just to show the power balance mechanism and hence the frequency control in the system. These are a few THD of currents. THD you see here, as far as the voltage profile is concerned, almost zero THD is there. Pure sine waveforms coming from the generator. The load side THD high because it's a square wave. It has maximum THD, and you see the source side sine wave, so the THD is very low. So this is just to show you the THD profiles, harmonic profile of the currents. Now this is all about a few observations, a few study which we have made on the wind energy conversion systems using squirrel cage machines, either in a single phase arrangement or a three-phase arrangement. But if you see the wind generation, especially for large scale, mostly the machines which is used is a slip ring machine, which is a doubly fed machine and more popular as DFIG. So in DFIG, also we have some work, and I may like to show you quickly the uh, power generation in especially grid connected mode through DFIG, because DFIG doubly fed induction generator are the machines which are coined using slip ring induction motors. So I hope you know, in a slip ring induction motors, you have a three-phase stator winding, you have a three-phase rotor winding. So this machine can be well utilized to feed the grid from stator and rotor both. And depending on its operation, whether the machine the wind speed is low or high. If the wind speed is lower side, the machine may operate under subsynchronous region, and if it is a higher wind speed, machine may goes in a super synchronous range where the rotor can feed power to the grid. In subsynchronous mode, it's usually drop power through the rotor. So there is a popular operation of DFIG, subsynchronous, supersynchronous mode, where operating especially in supersynchronous mode, you will see that negative slip may ensure that the machine even generate power through rotors. Stator could be directly connected to the grid. The rotor side converters are required to control the rotor currents and to ensure the variable speed operation of these generators. So the beauty of this DFIG is that even the wind speed has variations, you are able to maintain power transfer from both sides through control of converters in the rotor. Again, the rotor side powers, since it is simply a slip power, the power is less, just 30% of the stator power. So the rating of converter, etc., are lower in this rotor side. A stator directly connected to grid, so no converter is required there. So you see that way you can save some cost, and also you can feed more power to the grid, so more efficient operations. So I have just tried to include few slides related to DFIG as well. Hope you are able to see this. These generators also wind driven, so wind turbines are there. I hope these are the standard characteristics of a wind turbine. You can see the power generated from the wind turbine. General equation we saw yesterday is proposed is depends on the velocity of the wind. So wind velocity, if we consider in the range 5 meter per second to 12 meter second, you see the maximum power which comes out changes. So you see, if you want to extract maximum power from the wind turbine, we have to track the peak and through a MPPT algorithm here also. So as you see, in case of solar system, you might have used MPPT algorithm to extract maximum power from solar panel, and there we use a boost converter to ensure this implementation of MPPT. Similarly, MPPTs are also used for extracting maximum power from wind turbine because of these peculiar characteristics of the turbines, which where the peak power increases with increasing wind velocity. In fact, in real time, you all know that every wind turbine has a cut-in speed and a cut-off speed. This 12 meters per second usually happens to be higher speed, cutoff speed. Lower speed, maybe this range 5 meter or 6 meters. Average speed around 10 or 9. So the speed variation, if you see, is quite significant. And if this speed variation directly reflects in the output of generator, the power fluctuation in DFIG will be high. So in spite of such a wind generations, variation in wind speed, we try to ensure the power generated from generator is synchronized with the grid and the fluctuation is not very significant. So that is what is the role of the converters which are used in the side. Now, wind energy conversion system, as I said, this class of generators we have already discussed. Other class is this one, wound rotor machine based generation or DFIG based generation. Permanent magnet synchronous generators also used, but again, the performance of the generator for variable wind speed is not that much attractive as is in DFIG. So PMSG also costly machine with respect to induction machines, if you see. So broadly, you see that for small power generations, even these SCIG squirrel cage based generators can be adequate, but for large power, bulk power generations in wind applications, you see that DFIG and PMSG are more common. However, initially, synchronous generators are also in practice, but nowadays you see with the advancement in power electronics and all, DFIG is more popular. So these are just a picture of few turbines. You can see wind turbines are broadly two category. One is the vertical axis turbine and other is a horizontal axis turbine. So these are just wind farm picture of real picture from Quebec, state of Canada, showing you the horizontal turbine and vertical turbines. So if it is a horizontal turbine, you see it faces the wind speed directly, perpendicular. In other way, it is just opposite. These are just a few diagrams of your turbines. You see the turbine has a arrangement where you see it has a tower and on the top your generator system is attached with the axis of the turbine. So this entire thing you see is called neck, and in the neck every generator and other electronic parts are all enclosed. So you see in the wind generation system, the generator is not on the ground. The generator is on top of the tower and it is directly connected to the axis of the turbine. These two class of turbines, what I said, vertical axis and horizontal axis turbines, have their own advantages and disadvantages mentioned there. As far as vertical axis turbines are concerned, you see they have disadvantage that aerodynamics of turbine is little complex. Optimal power capturing in vertical axis turbines is difficult. And that's why you see vertical axis are not more common. It is the horizontal axis turbine, which you commonly see on this picture. In this picture, this is more popular. Most of the wind farm, you see this picture. So these are just about the turbines which are used for the different class of machines. Now, wind energy conversion systems, which are mostly grid connected, classified in 3-4 category. You see, one is type 1. The type 1 is wind energy conversion system, which requires a squirrel cage based machine and for fixed speed operations. So you see here you have a generator, and you see the rotor of this generator is connected to the turbine via a gearbox, and well, so you see here the type 1 configuration we have shown you. It's basically for fixed speed operations. And this is the arrangement where the squirrel cage machine, so it generates from rotor side, and you have a bypass switch, capacitor bank for running this machine as a for excitation for these machines, and through transformer it is connected to the grid. Now, since it's a fixed speed operation, here you don't need any converter. This happens to be a very elementary and arrangement, but not much popular because this requires, soft starter, bypass switch and all, and again ensuring variable speed operation is not possible here. Type 2, if you see, is basically a semi-variable speed, and this involves a wound rotor machines. A wound rotor machine means you have a squirrel cage, you have a slip ring induction machines where there is a 3-phase winding in the rotor side. So if a rotor side 3-phase winding is there, you have a provision to insert resistance in the rotor, and hence they control the rotor current, and that way you can control the turbine speed also to some extent. That's why a variable speed up to 10% you can control with rotor resistance. This happens to be, you can see, a very common arrangement in slip ring machines. I hope you all know that in a 3-phase slip ring induction motors, if you want to vary the speed and torque, the rotor resistance control is effective, but it is not an efficient arrangement because you have to waste power in the rotor through resistance. But yes, through this you can have a control on the speed. So even 10% variation in speed you can adjust, and you can generate power, you can feed to the grid. So this is called type 2 arrangement. Type 1 arrangement is almost a fixed speed operation. You see, fixed speed means the variation in speed just 1% here. Whereas here you see it is just 10%. So this type 2 based machines are being manufactured by Suzlon Energy up to capacity of 2 megawatt, very common and commercially available. With this, Vestas also has a 2 megawatt such arrangements where you have turbine and WI wound rotor induction generators. Another option is this type 3. Type 3, if you see, is again wound rotor induction machines. but the rotor side is not a resistance, it is a converter. And here you have a provision to change the speed up to 30%, plus minus 30%. So that's a quite good margin for speed variation. And this is why I said that this is the class which is now more commonly used, where 30% slip you can allow, and hence 30% of stator power you can generate through even rotor. Stator directly connected to the grid. Rotor side converters need to control the rotor current and hence the electromagnetic torque of the generator, and ensure that the power quality of the stator and rotor both side is adequate. But yes, if the speed is on lower side, obviously it gives you the subsynchronous speed operations, and in those cases the rotor may draw power from the grid. So that control bidirectional power transfer provision must be there in that converter which is placed in the rotor circuit. Such machines are very commonly used. Commercial machines of rating as high as 5-6 megawatt, very common, and single machine. And the converter rating, you can understand if the rated power 6 megawatt, just 30% ratings of converters are required. So obviously the cost of converters will not be much high. Another option is the type 4 wind energy conversion system, if you see. And type 4, you see here, we don't use any induction machine, rather we are using a PMSM, permanent magnet synchronous generators, PMSG we call. And PMSG, I hope you know, the rotor side has a permanent magnets, and stator side you see has a 3-phase winding. So such machines, if you see, are using for wind energy applications. You need to have a full capacity, 100% capacity converter, which will directly connect it to the stator and hence the grid. So this converter is operating at its full capacity. It has a capacity as high as the generator capacity. So obviously the cost will be high. The power devices rating, etc., will ensure a higher cost. So, but yes, PMSG based generators are commercially available. I hope you might be aware. These Vestas and the Inran are the two world leaders in wind energy equipments, and they have made such generators of as high as capacity 7.5 megawatt, 5 megawatt, and Vestas 3 megawatt generators are now commercially available and are used for commercial generations. So these are very broad classifications of doubly-fed machines or squirrel cage based machines, and accordingly we can classify them either a type 1 system or type 2 system or type 3 system, or if it is a permanent magnet based type 4 system. I have also few slides related to the converter controls. This is a PMSG based generation. So as I said, you have a turbine and you have permanent magnet synchronous generator. So you have a full capacity bidirectional converter. Here you see you have one grid side converter, you have the main site converter MSC, where the PWM control under vector control operation you can operate it. This grid side converter has one major role to maintain this DC link voltage. So this GEC grid side converter senses the DC current and also through its controller try to maintain the DC link voltage. And at the same time, so that if there is any fluctuation in wind speed, the DC link is still maintained and the power quality is ensured. So this is a broad a block diagram of a normal PMSG control. These are the few detailed diagram of the same circuit. MSC control, I mean the enlarged version. How do you find the real and reactive component of currents, alpha beta transformations, and finally how we use space vector PWM technique for MSC side converters, and how do you maintain the DC link of grid side converters. So these are the two blocks which are used to control these two converters, grid side and the main side converter, and ensure power transfer in PMSG based generations. We have few slides related to the control of DFIG also. So as I said, the DFIG has a scope to operate 30% of variation in wind speed. So you can understand that wind speed variation may be from 70 to 130%, plus minus 30%. For this wind speed operation, this machine also involves gears and bidirectional converter, as I said, in the rotor side. So through a transformer, the rotor is connected and stators are connected to the blade. The blade size, hub height of these wind turbines could be as high as 133 meters if you have a generator with capacity around 3.3 megawatt. So you can understand that it's all a very bulky arrangement. Even a 3 megawatt DFIG of Suzlon require a wind turbine of such a high blade length, that is 133 meter, you can imagine, and the tower which support this turbine almost a height of 140 meter. And if such bulky arrangement need to be installed to a place, because you also know that the wind potentials available are very usually at difficult places, maybe at a hilly place or maybe in the near the seashore. So if it is a hilly area, on top of wheel you have to install such a heavy structure. Carrying such a structure to top of the hill is also a challenge. So those real-time challenges are addressed through the mechanisms, but you can understand that this wind-based generation is not a very compact system. It's a quite huge system, but yes, it has its own advantage. The advantage is that if it is a DFIV based generation, the converter rating typically just 25 to 30%, because you have to you can transfer only slip power available in the rotor, which you all know happens to be S times PG. S happens to the slip of the machine, so slip 30%. Accordingly, the rotor side converter reduces, right? Rating of converter reduces. Improved efficiency due to reduced losses in power electronics. Yes, we are operating at low power, 30%. Losses are relatively less. Overall operation is good. Suitable for high power applications, including recent advances. Bidirectional flow of reactive power flow. So the rotor side converters must have provision to transfer power from both way, grid to rotor, rotor to grid. Fault right capability during network disturbance is a major issue in DFIG. So, and these chances are also more in case of DFIG. Few challenges. Flexible four-quadrant operation possible in DFIGs. Well, so these are just, as I said, the frequency of grid voltage is constant. So irrespective of wind speed, the rotor speed, you have to adjust as per the real and reactive power demand in the rotor side. As I said, you have a margin of plus minus 30% wind variation here. So that will make your machine to either goes either below synchronous speed operation or above synchronous speed operations. So if it is a subsynchronous speed operation, the stator generate power, but part of it has to be fed back to the rotor. In super synchronous, you see the rotor and the stator both are able to produce power to the grid. So that's the main benefit. If it is a super synchronous speed, you are operating, wind speed is adequate, higher side. You can operate in super synchronous. You can feed power from both sides, stator to rotor, and so on. Magnetizing current is supplied by the rotor winding because you see in DFIG we are not using any capacitor anywhere. Where in SCIG you saw there we were using some capacitor banks to provide the reactive power magnetizing current to those machines. So in all DFIG, the magnetizing current is supplied by the rotor winding itself. Stator will only have torque current component and hence it able to ensure a unity power factor operation on the PCC, the point of common coupling. So that's the major benefit, that with the rotor current only you can control the reactive power, magnetizing power requirement of the generator. Now the control of the rotor side converter, grid side converters, again there rotor side has to do two tasks, rather three tasks. The first is that control of torque and flux of the machine through rotor current, active and reactive power flow of the machine through rotor current, and if there is a requirement of MPPT also need to be implemented through RSC. GSC has a major requirement, grid side converter, that is what is shown here. You see this one, the rightmost. The grid side converter has simply to meet the DC link, maintain the DC link voltage, and also to ensure UPF operation for either side of power flow. Because you saw that if it is subsynchronous operation, rotor draw power from the grid. Other way it's supply power to the grid. So in both cases, it can ensure a UPF operation through GSC. So GSC has two tasks. RSC has three tasks. This is just a type 5 based, this in fact we could have discussed earlier while classifying the WEC systems. And these are few just slides. What are the trends in wind energy conversion systems? So it's a vast area. It's complete spectrum which requires the knowledge of electrical engineering, mechanical engineering, because the turbine itself, aerodynamics is very complex and requires a lot of knowledge, mechanical. And one generator you want to operate in grid connected mode, you must have knowledge of the grid stability, grid code, etc. That is what is the domain which is important. And control theory, you have seen a lot of control algorithms are required to operate these converters especially. So broadly, you see these four areas, knowledge of these four areas are important is for the engineers who works on WEC system, that is wind energy conversion systems. And if we look as far as electrical knowledge, then obviously you should have a knowledge of power electronics devices, converters, electrical machines. As far as mechanical knowledge, you need to have idea of gearbox, drivetrain, turbine blades, and its associated aerodynamics. As far as power integration, power system, as I said, grid code is an important area nowadays because whenever you integrate renewable energy, you have to ensure that grid codes are honored. Similarly, if it is a wind farm, onshore, offshore, how do you connect to the normal grid? How it can be connected to a radial system or so. So all those power system typical issue you need to keep in mind whenever you operate WEC system. As far as control theory is concerned, you see you must have knowledge of control of the wind turbine, pitch angle control and tip speed ratio. All these fine issues you need to address. Control of power converter, wind generators, those algorithm part also important. So this is just a slide giving you a broad spectrum of knowledge you need to have when you want to work on WECS system. These are few recent advancement which the few slides I could get, I try to show you. See, installation of a wind turbine, very challenging task. Mechanical structure may fall, and it will not, and it will lead to a lot of economical losses, So I hope this we have already discussed a lot. Switching devices, we have their own challenges, and these are the mostly silicon-based devices. But nowadays, I hope you know these class of devices, wide band gap materials are becoming more popular. Gallium nitride and silicon carbide. Gallium nitride is relatively costly, but silicon carbide is now becoming more popular because these materials are giving attractive characteristics for switching devices, especially high frequency operation and low conduction drop and all. So these devices will be the future devices, especially for the converter technology, which will be further enhancing the overall efficiency of your WEC systems. Silicon carbide devices have exhibited success more than 1200 volt. So you can imagine that even the wide band gap devices now available commercially at 1200 volts. So applications where you need a DC link of 700, 800 volt, these devices will support those applications. Power converters, hope you are aware, many new topology coming every day. Matrix converter, I hope now is an old one, but yes, it has its own advantage. You might be knowing. Control of power converters and wind generators. This is area where you need to know what is vector control, direct torque control schemes, because these are the mainly two schemes which are actually used to control these two-side rotor converters, or even in FPMSG also. And as far as the turbine side is concerned, the wind profile, etc., are also forecasted, and accordingly, the design, turbine performance are optimized. These are the few advanced area where one can focus, especially for the research and other applications. Wind speed estimators using neural algorithms. So there are a lot of data available from different sites that particular location, what are the profile of wind over a year, and based on those you can forecast the wind potential, wind power generation and all. So finally, I can come to the conclusion that the objective of this webinar was to provide you a general exposure related to research domain of distributed power generation, and more specifically an application to microgrid. Basics of induction generators. I mean, how do we generate power through induction machines, whether it's squirrel cage machines or slip ring machines. State-of-art distribution system configuration and mathematical modeling of some of the recently applied control techniques, especially adaptive control technique, which you have seen how much effective it is, especially in uncertain environments. Some simulation, some hardware experimentation also I try to show you just for addressing the new algorithms, effectiveness. Overall, it will be set a tuning of research student in the domain of reliable and futuristic distributed power systems. So there is a good scope to work in this domain, especially for research scholars, whether you focus on converter topology or control algorithms or the part of the machine or even the turbine side, a huge scope lies there. So this is related to the DFIG side machines, especially different type of classifications and the class of machines which are used in all these type 1, type 2, type 3 and so on. Most common configuration is state-of-art emerging wind turbines profile, structures were also shown and discussed. So these are the just a few observations related to my today and also study presentation. I hope this is all from my side, and Asutosh, if you are available, we can go as you advise.
Hello.
Asutosh, hope you are there.
Yes, sir. Yes, sir.
So I think from my side it's over. These are just few references and all. And if you have any question, we can.
Hello.
Yes. Yes, so you are audible, Asutosh.
My camera is, but I hope so. Am I audible?
Yes. Your voice is clear. Now, if there are any issue, we can discuss. Otherwise, I think you may start your next session.
Yeah, there are few questions, sir, but questions are, I think so, related to protection. Mr. Ravindra Kisan Rao Mankar, I think so, he is working in power system protection. That's why questions are somewhat, I feel so, somewhat different area. Actually, he is asking about
something which is directly related to my presentation. I can address. Yes. Otherwise, you may conclude.
Yes, sir. Now I would like to, I think so, if there is any question related to the presentation, I invite participants to put in chat box. I will ask from sir. Still, we have 2-3 minutes. If you are interested to ask the questions. But I think so. There is no question. One question is, can we get MATLAB models? Mr. Kausal Kirit Bhai Bhatt is asking. Actually, MATLAB models cannot be provided directly, but if any help is required, I think so it can be provided. And basically, in the MATLAB Simulink demo, a few models are available. So things can be learned from there also. Just I am giving the answer on behalf of sir.
Yes, that's very much true, because MATLAB model is basically a proprietary thing of the research scholars who have developed them. So
Yes.
We can't say anything on that. But yes, if someone is trying to do some work, wants some intermediate help, we can always connect the concerned persons and they will help them.
Yes, sir. And there is no, I think so, there is no further question. Now I would like to invite Mr. Divesh Parmar to give the vote of thanks to Dr. Masudan Singh, sir. Divesh.
Yes, sir. Hello, sir. Am I audible?
Yeah, you are audible.
Respected Professor Dr. Madhusudan Singh, sir, on behalf of Electrical Engineering Department at Government Engineering College, Bharuch, I would like to extend our heartfelt thanks for the exceptional lecture you delivered on microgrid configuration, operation and control with a special focus on a wind turbine-based microgrid. During this faculty development program, your expertise coupled with your clear and engaging explanations made complex concepts accessible and relevant to all our participants. Your detailed insight into microgrid design and control strategy were invaluable, sparking deep interest and insightful discussion among all attendees. We are also grateful for the time you took to address the participants' queries, providing clear, satisfactory answers. We truly appreciate the time and effort you invested in preparing and sharing your knowledge with us. Once again, thank you for your invaluable contribution to this FDP, sir. Thank you so much.
Thank you, Professor, and thank you, Asutosh, for inviting me. And what little knowledge I have on this topic, I try to share. But it's all an emerging area. Every day, researchers are adding something, and those who work in this area, they can appreciate those changes happening. So thank from my side to all the participants also for their patience hearing, and wish you all the best. Thank you.
Thank you very much, sir. It's our pleasure to have with you. And the participants definitely have got very much from your session, and they are motivated to do something new, and they have some direction from this session, sir. Thank you very much for extending your time here, sir. Thank you very much, sir. Thank you. Namaskar, sir. Namaskar. Now, participants, we are going to start next session, and expert has already joined. Just I would like to introduce our session expert. For today's second session, we have a very distinguished faculty member and our beloved professor, Professor Dr. Bhavik Suthar, sir. And I am very much associated with sir since last 2 years in one of our common PhD student. And it's my pleasure, sir, to be working with you. And it's our pleasure, our participants' fortune to have you as an expert here in this session. We are very happy for you, sir, and for the participants. Now I'd like to introduce Professor Bhavik Suthar, sir. In very brief, he is very humble personality first, very kind human being. Sir has completed his PhD in 2008 from IIT Delhi and currently working as a Senior Professor and Head of Department, LE College, Morbi, Gujarat. He has also worked as Head of Department at the prestigious LD Engineering College. That is one of the most prestigious engineering institutions of Gujarat state. So sir has worked as a HOD in that college from May 2015 to January 16. He has also served at ACPC, that means Admission Committee for Professional Courses at the state level, as an officer on special duty, that is OSD. He had worked as a professor in Electrical Engineering Department at GEC Bharuch from June 17 after getting selected by direct GPSC, Gujarat Public Service Commission. That means sir has become professor not through promotion but by GPSC selection, open competition. He is holding an additional charge of principal at GC Bharuch since 2021. He has published more than 39 international and national papers, general papers. He has 3 PhD completed research scholars worked under him and has guided 18 ME dissertations, and currently 7 PhD students are working under Professor Suthar sir's supervision. He is actively involved in the research in the area of power system analysis and application of artificial intelligence to the power systems analysis and dynamics. Now, directly, I would like to invite sir with just from very brief introduction from my side due to lack of time, and 3-4 minutes is not sufficient to introduce sir. Sir's contribution is immense in our system. We are very much thankful to have sir in this session. Thank you very much, sir, for joining us.
Thank you, Doctor. Thank you, Professor Asutosh. I hope I am audible.
Yes, sir, you are audible. You can share your slides.
Okay. So I will, first of all, I will share my slide.
And sir, Doshi sir has given his wishes to you. He could not join due to some family functions. He was involved there. That's why he told me to extend his blessings, his wishes to you. Greetings.
Thank you. Thank you.
Thank you. Yeah.
I think my slides are visible now. Hello.
Yes, sir. Yeah.
Yes, sir, it is visible.
Okay, thank you. Thank you. So first of all, I am thankful to Electrical Department of GEC Bharuch for giving me the opportunity to talk to the participants of ATAL FDP. Thank you very much to head of the department, principal, especially the coordinator, Dr. Ashutosh, and his team. So in this presentation of microgrid control and stability, I will be discussing some of the challenges, some of the strategies used, and some research areas where somebody can do his research, his or her research. So the outline of the presentation will go like this. First of all, we'll discuss very briefly, very briefly about central power grid. Then what is the difference between the earlier grids and modern power grid. Then we will see something about how the grid evolution has taken place. We'll discuss about the renewable energy sources in India and how it is integrated in the grid and microgrid. We'll discuss about some characteristic of the ideal grid, and then we'll discuss the challenges and operating characteristic of microgrid and how it can be operated with the in the grid integrated mode or the standalone mode. Then my favorite area is stability, and I will be discussing something about the stability of the grid and how the stability of the microgrid differs from the conventional stability study of a power system grid. And then one or two slide about the participants who wish to do the research will have some slide about discussion of research areas in this particular microgrid and grid connected areas. And then stability, reliability and management of microgrid and grid. So first let us discuss about the grid. So this is the general concept of grid which you can see in this slide. A very fundamental thing when we ask our UG students what is grid, then he will say some generating stations, some transmission lines, some distribution systems, and then some load. So starting from generating stations to substations and then load, this form the grid. And this is a previous one, but the modern grid we'll discuss in the next slides. But if we discuss about the grid configuration in India, then earlier you all must be knowing, but this is just for reference. Earlier we had a different 5 grids, and one by one they are connected. And in 2014, thanks to Power Grid, that we have one nation, one grid, and one frequency. So in 2014, the entire nation is connected in a single one grid. So this is just a grid evolution. And when we talk about the installed capacity in a power system in India, and we talk about the contribution of the renewable, then this data I have taken from the NITI Aayog website, and this data is of November 2024. So in November 2024, just 1 or 2 months back, it is a total installed capacity of India is 457 gigawatt, and out of 457 gigawatt, the contribution of renewable is 209. And you can see this in the bar chart how it has grown, and in the circular chart you can see the contributions of different generating stations, like what is the contribution of coal and what is the contribution of wind, solar, small hydro and everything. So this data just I have taken from the NITI Aayog website, and this is just for your reference that how the renewable is getting integrated into our normal grid. So when we talk about the grid nowadays, it has changed. What we have seen in my first slide is not the case nowadays for the grid. For the grid, generating stations, earlier we had certain large generating stations of very few numbers. But nowadays, you can see there are many generating stations, many DERs, distributed energy resources, with smallest capacity in terms of kilowatts to the maximum capacity of gigawatt up to. So generation trend or generation mechanism has changed. Similarly, the transmission mechanism or market mechanism has also been changed. Earlier we had a centralized, or we can say vertically integrated power system where the entire control was with only one entity. But now we have a different transmission, generation, distribution. Everything has been different, considered as a different entity. Now in distribution, earlier it was one direction, like they are getting the power from the transmission and they are giving the power to the distribution substations. or consumers or load. But nowadays it is not like that. From the DDRs also the power is being paid to the grid, and from the transmission systems it is being given to the another consumer. So this is the change in the distribution systems. And finally, the consumers. Earlier, the consumers were just consuming the power. Now, the power is being consumed by the consumers as well as it is generated by the consumers. And that is why nowadays they are also called the prosumers, producers as well as consumers. The second thing which I would like to mention about this talk is I will not be discussing anything about the power electronics side, but I will be discussing microgrid from the as a viewpoint of the power systems engineer. And most of this talk or most of the discussions in this talk will be on the from the power systems side. Okay, so when we talk about the modern grid, these are the change which has taken place, or the evaluation has been done in the grid. But when we talk about the grid or modern grid, what should the grid possess? What should it have? So what are the qualities? So first and foremost quality is grid should be available everywhere. Suppose I want to have consume the power, or I want to give the supply to the load, then the grid should be available nearest point, at the nearest point to the load center. That is the first and foremost requirement. If it is not there, then there can be the solutions, but this should be the ideal condition. Second thing is because as we all know that our system is a constant voltage source system. It is not a constant current source system. So whatever may be the load connected at the grid, but the voltage available at the grid or voltage from where we take the power should remain constant irrespective of variations in the load. The third thing is, when we talk about the availability of the AC power from the grid, the voltage waveform available should always be the sinusoidal. If it is not sinusoidal, it will create the another problems of harmonics and operation, many various operating problems that we'll discuss in next slides. But ideally, the waveform should be purely sinusoidal. The next quality of the grid is it should have the constant frequency, irrespective of load variation or a generation variation. Its frequency should remain constant. The short circuit ratio, basically it decides the strength of the grid, and this also should be considered as one of the important parameter in ideal microgrid, ideal modern grid. The next quality of the grid is the quantity of the power which the grid should be able to transfer. Like suppose I have excess power of certain amount at one place in the total area, then our grid should be able to transfer that power from that particular area to the area where the load requirement or power requirement by the load is more. So it is basically known as the wheeling of the power, how much power can be transferred using the network, transmission network. So it should have very good power transfer capacity. This is just a small introduction about the grid and what should be the ideal grid and how it has been evolved. Now we'll discuss about the microgrid. So in the microgrid, first point which comes in our mind is what are the components? What should be there in the microgrid? So basically, microgrid is a grid form for the small or a particular area where it should have the generation. Now the generation in the microgrid can be of two types. It can be generated using the traditional generating power stations, or it can be generated from the renewable energy sources. So if it is from the traditional generating stations, it can be known as a dispatchable power. And the another one, when we use the REC, it is non-dispatchable. Dispatchable means whenever you wish, you should be able to control the power by your own wish. But when you have the RES, there are different things which we'll discuss in the later part. But distributed generations, two types, dispatchable and non-dispatchable. So renewable energy sources are there. Then the next part or next thing in the microgrid is the energy storage systems. In the microgrid, as sometime or another way, it is used for the standalone mode, and when it is used in the standalone mode, microgrid is used in the standalone mode, then in that case it is comparatively difficult to control the generated power and the supply of load in that particular area. So for that purpose, for excess energy storage, we should always have the energy storage system. Then we should also have the control for this particular microgrid. So we should be able to control all the RES or ESS or generations, distributed generator, conventional distributed generators. So all these things should be controlled, and it can only be controlled if we have the proper communication link between these generators or renewable energy sources or ESS, and we should have the information about the load and proper communication network. And this can be done using certain interfacing devices. So these interfacing devices also be used to interface the microgrid with grid. Of course, load should always be there in the microgrid. So once we have discussed the components or what are the main parts in the microgrids, let us discuss why microgrids are required. So what are the benefits, what we get by having the microgrid? So first thing is, by having the microgrid installed in an area where the load is more, so it can supply locally. The power from the microgrid can be supplied locally, and the burden on the transmission line can be reduced. So losses in the transmission line can also be reduced. Second, it can cut the emissions, because the generations required to be transmitted can also be reduced, and we can use the RES also. Then the another benefit of having the microgrid is it increases the reliability of a grid in certain particular area or in certain conditions. This can be done, or this benefit can be obtained by using this microgrid in a grid support mode that we will discuss in the later part. Then there are certain areas where it's a very hilly area, or it is very difficult to get approach to those particular areas, some army area or some border area or some hilly area. So where it is very difficult to lay down this transmission system and have the access to the grid. So this kind of area can also be electrified using this microgrid. Then the another benefit of microgrid is peak load reduction. By adjusting the load from the microgrid, the peak load in a particular area can also be reduced. The demand side management is a one important aspect where the power systems can also be managed from the consumer side, from the load side, from the demand side. So having the microgrid, this has become possible to manage the grid from the demand side. The consumers' participation can be increased in e-generation, as I told you in the previous slides, that the consumers can become the prosumers and they can also participate in the generation also. So, and the final benefit which we discuss here is the benefit is the critical load supply. So some critical loads which has to be supplied all the times can also be supplied using the microgrid. If the supply from the grid is not available for certain time, then this microgrid will supply this critical load all the times. So these are the basic benefits of the some simple benefits of the So these are the some of the benefits of the microgrid. Now we'll discuss about how the microgrids can be classified. So first is whether it is this microgrid is being erected in the particular remote area there is no access of the grid. So this kind of microgrid is known as off-grid microgrid or off-grid operation of the microgrid. The another one is a campus microgrid. Like this kind of microgrid can be installed or can be we can have in a particular campus or a small area or small territory. The community microgrid is considered as when we have 2 or 3 or 4 campuses nearby, and when all these campuses are connected together and we have a microgrid for that, that is basically community microgrid. Then based on the voltage level at which the microgrid is being operated, we can classify. There are different types of different voltage levels at which the microgrid can be operated. Sometimes we have 11 kV grid, sometimes we have 400 kV, something like that. Then depending upon the power capacity. See, IEEE standards we'll discuss in the next part. IEEE recommends the maximum grid capacity of 10 MVA. But higher is also possible. They can be connected, but we may have the grid capacity of 10 megawatt, or we may have the grid capacity of 1 megawatt, or even some kilowatts also. The another classification is whether the grid is supplying the AC voltage or it is giving the DC voltage. Depending upon that, we have AC voltage, AC grid or DC grid, and sometimes we have both the buses in the same grid. If we have a DC load, we will connect our load to DC bus. If we have a AC load, we will connect the load to the AC bus. And so we have a hybrid grid. And next is depending upon the types of the distributed generation used, we can have only RES or we can have only conventional generations, and based on that we can also have the different types of microgrid. And another is a feeder area microgrid. It is up to 20 megawatt, and if it is more than that, then we need a substation for connecting the microgrid, and it is known as a substation area grid. So we have a feeder area microgrid and substation area grid where the power level of the grid is more than 20 megawatt. So this is a simple block diagram of a AC/DC microgrid where we have a distributed generation, DC distributed generation or AC distributed generation. We have a storage element, and then we have AC load and DC load. So this is a simple block diagram of which are the main components in the hybrid microgrid. So this is just basics of microgrid. Now we'll discuss about the RES, because in microgrid we have different renewable energy sources. So when we have a different renewable energy sources, and if it is integrated in the microgrid, then in microgrid the characteristic of RES is slightly different. It is not same as the conventional sources. So what are the main important points for the RES? The first point is market development for RES. You know, before 10 or 15 years, nobody was, or very few people were using the solar or wind. But nowadays, everybody is using the RES. We have our rooftop systems of solar or wind turbines are also being installed. So market development for RES is very dynamic. The procurement mechanism for procuring the powers from RES is changing very drastically. Initially, the price given for unit generation from the RES, like if you generate 1 unit, the price given by the utility, and nowadays price given and the mechanism of calculations. First, initially we had only two, A and B. What is the power consumed by you and what is the power given by you, and then simply algebraic sum, and then you will get the bill. You will be given some amount or you will be getting the bill. But nowadays it is ABC. It is different. Then incentives also, it is changing very dynamically. The contracts are also very different from the market point of view for RES. For RES, training and awareness is also required in a huge amount, because you know, in our institutes also, you must be facing in your institutes also, there are many companies visiting for solar and wind, but the candidates are not available. Even their knowledge in this area is also require enhancement, or very fast in knowledge gathering is required in this particular area. Then operating mechanisms, converters and inverters, power electronics people, and then the converter, inverter control topology. Professor Asutosh and his team is working in this area, and they are coming with new ideas, and in entire world they are doing some research, and it is very fastly changing. So operating mechanism of RES or power electronics involved between RES and grid is changing very fast. The owner and utility should have the direct communication link, or this communication link is also very important for the market viewpoint. And people are talking about expert system, AI, and smart grid, all these things for RES plant operations or for the grid optimization where we have RES. So these are the some of the important points of RES. Then what are the challenges? The first challenge in the renewables, which is used in which is used in the microgrid, are location specific. So your renewables cannot be used everywhere. You should have certain weather conditions where you can use the renewables. The second challenge is the harmonics and nonlinear operation, or the load dynamics where it is used. The dynamics of load also affect the operation of the renewables. So these are the important challenges: harmonics, nonlinear operation, load dynamics. Then the next one is the control parameters. Which control parameters we have to use for the its possible power transfer, real and reactive power transfer between the grid and renewables, or grid and load, or renewables and load, or energy storage systems. So control parameters and its usage is also a challenge. The RES generation may not be transported over a longer distance in a real and reactive power, but it can be transferred or transported with certain constraints. So, when we want to transfer the particularly reactive power over a longer distance, it is very difficult. First thing is, it cannot be transmitted alone. If you want to transmit the reactive power, it has to be done with some amount of real power. Then and then it will become possible. And when we transmit the reactive powers at over a longer distance, it also creates the stability issues or voltage fluctuation issues or voltage regulation issues. The another problem with the renewables is its uncertainty in prediction. So we cannot precisely predict what will be the output of a solar or wind power tomorrow at 11 o'clock or 12 o'clock. It is very difficult to predict. And if it is predicted, the output available and whatever the predicted actual amount which is available from the renewables and the predicted output, both the things will be different. These things related to market operations, but I will not discuss this point right now. Then the characteristic of microgrid, how it is operating characteristics. So first thing is the stand-alone operation of a grid, where it is not connected with the grid, or the another one is a grid tied operation when it is connected to the grid. The second operating characteristics is diversified control mechanism over the conventional one. So when we have a conventional power grid, then there are straightforward rules using which you can control your generation, or you can control your reactive power or real power, voltage magnitude, frequency. But when we talk about the microgrid, and when we want to control the parameters or variables of the microgrid, its control mechanism is different. Voltage magnitude and angle control. Then frequency regulations. So in microgrid, when we operate the grid, in a standalone mode or a grid-tied operating mode. In both the cases, the controlling of the frequency is also related with some power electronics devices and these mechanisms. The most important characteristics of a microgrid or its operation is the inertia. If we have the conventional power generating unit DG in the microgrid, then for conventional power grid, it is no issue because it has the sufficient inertia. But when we have the RES, like solar, maximum participation of solar or wind, then the inertia is also there, low inertia is there. Its response time, we'll discuss about this response time in next slides. And when we talk about the operation of microgrid, power electronics controls or controllers are more important. Now, grid connected methods. How the microgrid can be connected to the grid. So there are three different connecting methods. One is a very simple method, that is direct connection of microgrid with the grid using the switch gear. There is only one switch gear between this microgrid and grid, and direct it will be used as a switch and it can be turned on or turned off. Second is a power electronics interface. So between the microgrid and the grid, there is a power electronics interface, power electronics, and which can be used to control also between the grid and the microgrid. And the third one is the static switches. So using static switches also we can connect the microgrid with the grid. The another thing is the monitoring, how to monitor. In the microgrid, the availability of the data at the control centers and the control of the variables of the microgrid is the main issue, because see, when you want to monitor the grid or a microgrid, you should have large number of data available with you. And once this data is available, how to design the controllers or how to find out the controllers. The another issue is the protection issue. Short circuit ratio, fault right through, that is one, we can say one specifications for grid and microgrid. So this fault right through capability should also be decided. Low voltage right through or zero voltage right through or high voltage right through, this capacity is specified. Then anti-islanding. So whenever we need to disconnect the grid, microgrid from the grid, or whenever we do not want that this microgrid should be disconnected and still it is disconnecting, so this kind of phenomena should not happen. So for that you have some certain mechanism for anti-islanding. Then automatic disconnection whenever there is a over voltages or there should be some, if there are some problems with the generators. And this could be avoided using the power electronics. Challenges, as I told you in the previous one, the IEEE recommends 20 MVA for microgrid, and if you have much larger load, you can use these pool of different 10 MVA, 10 MVA microgrid or certain spot, we can say. If grid voltage goes behind the set value, disconnect RES. Injection or withdrawal of the reactive power facility should be there. It should be able to provide the leading or lagging current with the grid waveforms. And the fast response, it should be able to give the fast response for frequency and voltage regulations. And for that, we have different grid codes and standards. And in India, we have CEA or CERC or SERC, which decides these grid codes or standards. If somebody wants to do the research in the area of microgrid or renewable energy sources, then this defining the grid codes and defining the standards is a very good area, because nowadays what happens, different country uses the different grid codes according to their environment or their conditions. And in India also we are using the grid codes or the codes given or different restrictions given by the CERC or CEA or SERC, but there is a huge opportunity of doing research in this particular area. Now we'll discuss about some of the issues of power qualities in the microgrid. So the first problem is the distortion of the waveform and displacement factor or the power factor. And nowadays the government has also implemented in some part of the country and implementing some another part of the country kVA based milling. And in kVA based billing, you will also have to spend money if you are using the non-linear loads. The another issue is a constant voltage magnitude or waveform frequency, reactive power management. The brownout means some part of the grid is not working. Load dynamics we'll discuss in some slides after some slides. So there is 2-3 slides for load dynamics. And this ride through capability. Unbalances means if we have a 3-phase supply system, then in 3-phase some of the phases or all the phases will not have the same phase angle and same magnitude. So unbalance is also there because of this RES or microgrid compared to the conventional one. So reliability quality is one of the qualities, the reliability. So reliability is also important. So these are the power quality issues with RES or microgrid. Then when we want to integrate the microgrid with the grid, the integration challenges are the network management, because sometimes we may have the sufficient powerful network available, but sometimes we have a neat network available, but it is a weak. So at a weak network, you cannot connect the grid, and if you connect, there are issues of integration. Ancillary services, there are certain services which every microgrid should be able to provide to the grid operator whenever they demand. So these services are also has to be provided before the microgrid is connected to the grid. Planning and forecasting is also the problem. See, if you have a normal generating stations and normal grid, this planning, and there is certain rules and regulations for planning and forecasting the load and generation. But when you have a RES and microgrid or RES in the microgrid, the planning of forecasting is very difficult because it depends on weather. Scheduling of each generating stations or each grid equipments, like each grid component is also the challenge. Availability of network we have already discussed. Pricing plays an important role, because when you have a when you don't have the demand of power in the grid, you will not be given much amount of money for your power generation. And if demand is more and you are not able to provide the power, then there are also some penalties. So pricing is also very important point when we integrate the grid with the microgrid with the grid. And then SCADA and data transmission systems. This is basically required to get the information about all the generating stations or all the load or all the other ESS and other equipments available in the microgrid or grid. So this data transmission or availability of the data at energy management systems is also important. And certain commercial issues are there. The final point is the stability. So this is the another part of the this lecture. The first part is what is grid, how it is connected, what is microgrid, how it is connected to the microgrid, and what are some simple or important points, or what are the challenges we have already discussed. Now, when we talk about the control and stability of microgrid, how it is different from the conventional one, that we'll see. So in microgrid, we have basically we have to control basically voltage, frequency, real and reactive power. We have to have the balance between the load and generation, and we have two operating modes like grid or grid connected mode and standalone mode. So there should be a smooth transition between these two modes, and then it should be, all these things should be operated economically. Okay. So if we talk about the control strategy for the microgrid, this is a simple microgrid. So you can see in this block there are three control blocks. One is a primary control, second is a secondary or a centralized control, and third one is a tertiary control. And these blocks are connected with communication links to each other. So basically all these blocks should be able to communicate with other blocks. They should be able to communicate with each other. And then we have one grid, and there are two things. One is the small things like ESS or different generating stations like PV or wind are connected to the bus. When they are connected to the bus, it is known as point of connection, POC. And all this power coming from by either primary control 1 or 2 or another synchronous generator, all these things. Then when it is connected to the grid, so this bus when connected to the grid, it is known as point of common coupling, PCC. So POC and PCC. POC means when we have a connection of ESS with bus, or when we have a connection of PV with bus, it is basically POC. This thing is PCC. And how this control mechanism is working, or what are the functions of all this control. So when we talk about the primary control, in primary control, it has to control four things. One, local voltage, local frequency, power, and real and reactive power. Means basically it is a power factor. What is the amount of, what should be the amount of real power and what should be the amount of reactive power. This is for a particular block or a particular generating RES, like one primary control for PV, one primary control for wind, one primary controller for ESS. Like that we should have the primary control. We have already discussed in the previous figure. Then comes the second controller, and that is the secondary controller. In the secondary controller, it is the regulation of the voltage or restoration of the voltage. So basically this block is responsible if there is a change in the voltage, it should be able to bring back the original voltage level by doing certain control actions. Similarly, the restoration of the frequency. Then the third one is the power quality control. It has to control the quality of power, everything, harmonics, real power, reactive power, power factor, everything. And then the final one is the synchronization and flow of real and reactive power from load to source or from grid to microgrid. So basically these two controllers, primary control and secondary controllers, will have this kind of functions. And when we talk about the time frame, then this primary controller should operate first. It is the milliseconds to 10 seconds, up to 10 seconds. And after comes the secondary control, where it should be able to operate within milliseconds to 100 seconds. The third one is the tertiary control. Now in tertiary control, it is the on top of primary and secondary control, and it requires the proper data, proper forecasting and planning. It does the work of the supervision. It also does the scheduling. So how much power will be taken from which generating plant, which RES, whether we need to get the power from the grid or we need to give the power to the grid. So this tertiary controller is responsible for doing this operation. And then optimization. So based on certain optimization objective functions, it will give the generating command to all the primary or secondary controllers. It will also do the function of load balancing. It has to be done and it is must. Load should always be balanced with the generation. Then some another points of the controllers are how fast it will work, in what time frame it should work. Like see, if it is to be operated in milliseconds and it takes seconds or tens of seconds, it will create the stability problems to the system. So time frame of operation, speed of response, how fast what are the time constant of these controllers or these devices, how fast it is responding, and the requirement infrastructures. Basically, when we talk about the infrastructure requirements for these controllers, it is the communication skill, this communication links or data transmission or data collection, this kind of power electronics devices. In real-time operation, the microgrid control centers or microgrid controllers basically will have to do this kind of analysis. The first thing is the data collection and monitoring. So it has to take the data from RES, DG, ESSS or load data. It should have the load grid data. It should also have the weather conditions. From there, it will be able to predict what will be the amount of RES power available and planning. Data analysis, forecasting, the management. It should be also able to communicate for the market. Two types of energy market, ancillary market also. And there are constraints while doing these real-time operations. So when the microgrid is to be operated or is to be controlled, it is in connection with the energy management centers. When it is connected to the grid, it should be able to communicate with energy management system. Basically, it is a load dispatch centers. So energy management centers and the microgrid controllers, when they are doing the controlling of microgrid mutually, what are the constraints they face? So first constraint is the energy balancing. They have to always ensure the balancing. Second is the network constraint. Your network should have certain power transfer capability, ABT and TT, total power transfer capacity of the transmission line, TTC. So based on that, based on the network constraint, you should be able to transmit the power, not much more than that. Output limit of each of the generating stations or generating RES or DG in the microgrid. Demand response. So load response, basically when what is the load and how it is increasing or decreasing in a next time slot. So this is also the one of the constraint. And the reactive power support is the most important criteria or important point for the operation of the microgrid in connection with the EMS, because if you do not have the reactive power support, it will create the problems of the voltage fluctuations, and if it is not controlled properly, again it will create the problems of the voltage stabilities. Outages and interrupts, unexpected, but when we have outages or interrupts, the problems has to be solved. These are the constraints, and then market constraints. So this is the commercial thing. So fastest control should be islanding detection. Islanding should be detected very early stage, fastest. And in grid connected mode, when you are operating your microgrid in a grid connected mode, it is limited to ancillary services. Means it will work, your grid will work only as an ancillary service provider, because whatever the magnitude of the voltage the microgrid should have, or whatever the frequency it should have, it will be decided by the main grid. It is not independent. You want to keep your voltage this much or that much or frequency this much. No, it has to be governed by the grid. Whatever the grid requirements, according to those requirements, your frequency and voltage should be decided. Stability of microgrid in grid connected mode is a stability of individual components. So basically because see, the grid is like a very big thing. It has very high inertia. Compared to grid, your microgrid is a very small thing. So you cannot talk or you cannot do anything to the stability of the grid. It will run in its own way. But when you talk about the stability of the microgrid, it is your local stability of the local equipment. So local components or individual components in the microgrid will decide the stability of the microgrid when it is connected in the grid connected mode. So it is basically the stability of distributed generations or local load or motors or large loads, whatever is there in the grid. The next important point is, when we talk about the microgrid or RES, which is to be connected with the grid, what are the standards? So those standards are IEEE 15447 standards, and as per these standards, this is published in I think 2018 or 19. So as per these standards, the electrical power system area is divided into 5 parts. The first part is the area where you have only load. The second part is where you have load as well as the distributed energy sources. The third one is the distributed energy sources only, nothing else. And fifth one is the distributed energy sources as well as some new or added supplemented DER devices. Means it has some added power generation capacity along with the distributed energy sources which are fixed. So you can have both DER and supplementary with load or without load. So you can see in the block diagram, there are 5 different blocks and each one is defined like this. This is defined in IEEE 1547. We have already discussed what is POC and what is PCC. So these are the terms which we have discussed. Now this low voltage ride through or voltage ride through, high voltage, zero voltage ride through means it is the ability to withstand the voltage or frequency disturbances for a certain limit. After that, it should come to the specified limit, not the original one. It is good that if it comes to the original one, but it should come out of that particular disturbance. So this is the ride through. And when we talk about the voltages which we need to measure at PCC connections for any purpose in the standards. So if you have a 3-phase 4-wire supply, you have to measure the phase to phase and phase to neutral. You have to take both these voltages. If you have 3-phase 3-wire grounded system, you have to take the phase to ground and phase to phase. If you have 3-phase 3-wire supply, then it's only phase to phase. And if you have single phase or 2-wire system, it is phase to phase or phase to neutral. What are the standards for synchronization? So whenever the grid, microgrid is to be connected or RES is to be connected with the main grid, or when it is synchronized, while doing the synchronization, the voltage and frequency magnitude momentarily will change, because it is like just one car is moving and you are connecting one bicycle or small two-wheeler to the car, and both should run in the same speed. So while connecting, there will be a jerk. There will be a change in the voltage magnitude and frequency. So in this table, in this the IEEE 1547 standards, this whatever the amount of changes accepted has been given. So voltage difference, frequency difference, and power angle difference, delta. It depends upon the rating of the DER which we are going to connect. Then similarly, real reactive power voltage, how your DER should be able to provide. So let us say first operating mode is the constant power factor mode. So in constant power factor mode, your real power and reactive power should change simultaneously. Means if your reactive power is increasing and real power is not increasing, then in that case your power factor will change. So that is not the case. In constant power factor mode, both the real and reactive power should change simultaneously. When you have a voltage reactive power mode, your voltage and reactive power should remain fixed. When you have an active reactive power mode, there should be a certain relationship which will be given by the grid key. This is the relation of the active and reactive power mode which has to be followed by you when you are connecting the RES to the grid. So for 1% variation or 10% variation of active power, your reactive power should vary 2% or 1%. So accordingly, you have to make the changes. It should be there. And in constant reactive power mode, irrespective of change in active power, your DER should be able to provide the constant reactive power. So these are the different modes in which your DER should operate while connected to the grid. These are certain limits of active power change, how the active power should be transmitted or transformed from the grid to the DER or DER to the grid, and when there is a change, in what seconds or what time it should be done. Then this is the maximum and minimum reactive power which should be like the DER should be able to give to the grid, or it should be able to absorb from the grid. And as I was talking to you, it is a voltage right through is a, or any code, grid code, or any restrictions which has been there for the renewable integration or microgrid integration. It is different by different organizations, and it is used in different values in the different countries. So this is just a collection of which organization is giving this code or regulations in which country and what should be the amount. You can see it is different in every country and every organization, and that is why I am saying that this is the area where one should work or do the research. This is basically the unbalance in the voltages of all the three phases in the RES or grid connected. So now I will finish within maximum 10 minutes, and this 10 minutes I will discuss about the microgrid stability. So when we discuss about the stability of a entire power system, then we have a small signal stability or dynamic stability, then transient stability, then voltage stability, and why this happens or what are the controllers used in this particular stability. So these things are basically common for grid or a microgrid, but when we talk about the microgrid, how the microgrid stability becomes different than the stability of a grid. So if we discuss it, the first point is, let us assume or let us understand how the stability of a power system grid is being evaluated. So normally we have some equations, some modeling. So for power system we have power flow equations. For entire power system we have the equations. So these equations comes from the modeling. So we have a Y bus and we have the static load flow equations, and we solve these equations and we form the matrix, and this matrix Jacobian we find out, and from the Jacobian we find out the stability. So we do the modeling. While doing the modeling of a grid and while doing the modeling of microgrid, totally both the things are different. For doing the modeling of the microgrid, you have to model each and every component of the microgrid. The first and most important difference is the R by X ratio. When you have the load flow or grid modeling, we use the transmission network, and the value of X is considered much more than the R, and the static load flow equations are being done. But when we have a microgrid and when we do the modeling for the microgrid, the value of X is comparatively very small than the traditional one. So first thing is when we doing the modeling, R by X ratio plays an important role. Second is we have a model, different IEEE standard models for synchronous generators. But when we talk about the model of PV or model of wind, these models has to be integrated in the equations. And the availability of the models or the models which are being used by different researchers are again new and different. So you have to come to the conclusion that this model has to be used for this particular study or this particular microgrid, and then you have to form the equations, and then you have to try to solve the problems, try to solve the equations, and you have to design your controllers, and accordingly you will be able to find out the solutions of the stability of the microgrid. So this is basically the simple thing about the microgrid stability. Whatever we have discussed is for the angle stability. But when we talk about the voltage stability, and when we talk about the voltage stability of the microgrid, then see, the voltage stability is more concerned on the reactive power, because it is the reactive power which can control the or which can support the voltage at each bus. So you need to study the reactive power load or reactive power generation or reactive power limits of each of the components of the microgrid, whether it is a PV or it is a wind or it is a small hydro or it is a DG conventional one, or even other things. The second point about the voltage stability of the microgrid is the load in the microgrid. So see, load plays a very important role in the identification of the stability or evaluation of the stability, voltage stability of the microgrid. We'll discuss in the next slide. Then shading, under voltage load shedding. This comes last. Normally load shedding should not be done, but if you don't have any chance, then shading is to be done, should have been done. The tap changers of the transformers and voltage controllers, whatever the type of controllers you have been using. But when you use the voltage controllers and when you have the certain parameter of controlling it, like in terms of transformers, it is a tap changer, or if you are using the DC-DC converters or AC-DC converters, then we have firing angle or duty cycle or whatever type of controllers or you are using, and whatever the type of voltage magnitude change you are getting. So the operation of those things are very important. The another one is the protective devices or protection, voltage protection of the protective devices used in the microgrid, because whenever there is a protective devices operates, so basically whenever the protective device operates, what will happen? It will cut off certain part of the microgrid from the grid. So when some portion of the grid is out for service, either it is a load or generator or ESS or whatever the component, it will create it will have the impact on the other operating part, with other part which is already operating on the system. Okay. So I was talking about the load dynamics and load types. So this is simple. The PV curve or a QV curve, or in the x-axis we have P shown here, but it can also be applicable for the Q, reactive power. So see, whenever you draw the PV curve for the any load, at any load, if you have a good power factor like innermost curve, your power factor is 9.95, and in the second curve the power factor is unity. And when your power factor is improving, your curve becomes flat. So what does it indicate? Ki whenever you have the very good power factor, leading power factor or unity power factor, your PV or QV curve becomes flat. That means when the curve is flat, means you have the variation in the x-axis, but the variation in y-axis is very small. So what will happen if your load power factor is, let us say, lead 0.95? So in that case, whether you are drawing P2 power or P1 power or P2 max, the value of voltage or change in the voltage is very small. At the same time, if your power factor is low, like 0.95 lagging, so you can see these two voltage values. There is a difference in the voltage magnitude. So your voltage will specify, or it will tell that you are increasing the load and your voltage is going down, so it will create the problem. But if your power factor is very high, it is very good leading power factor, then you will reach to the critical point, and then you will have the, you will understand that the voltage is going down and now I will have some problem of the voltage stability. This is one point. Second thing is, when we have the different types of load, you know, there are different load modeling, ZIP model. Z is a constant impedance load, I is a constant current load, and P is a constant power load. So when you have a constant impedance load or a constant current load, your voltage magnitude going down is comparatively, for constant impedance it is very less, than for constant current it is more, and for constant power it is even more. And induction motor it is even more. So this blue lines is not a, they will not create the problem in the operation of the power system as far as the voltage stability is concerned. But when you have a constant power load or induction motor load, it will create more problems as far as the voltage stability is concerned, because your critical point or your collapse point will reach very early compared to the. So this load dynamics plays important role. Okay. Then we have the one standards or some standard to be followed for the reactive power available in the microgrid. Okay. How can we improve the stability of the microgrid? So first of all, we have to do the proper modeling of each component, then its linearization and its proper analysis. We have to have the stabilizers for DG. You know, we talk about PSS, power system stabilizers. They are used for the standard synchronous generators. But when we have DERs or DGs, we don't have sufficient amount of stabilizers available. Research is going on, but still we need to have more and good stabilizers for DG. The another one is the inertia, because in RES or microgrid, RES used in the microgrid, the inertia problem is there. So virtual inertia or emulators used, or certain algorithms are used which will work like a virtual inertia, and it will help in controlling. Then we have coordinated control. When we have the renewable energy source management systems, we have microgrid controllers, and we have SLDC or EMS, energy management centers. If we have these things and they are coordinating each other, then in whenever there is a requirement of stability, or whenever there is a requirement of reactive power movement or transfer or availability or injection or absorption, in a coordinated way it can be done and it will improve the stability. The next one is the AI. Artificial intelligence can also be used. There are many or very wide, very wide area for using the AI in the controllers for improvement in the stability. Power electronics, as we all know, we are using power electronics, but power electronics with certain controllers, certain algorithms will be useful for improving the stability. And final one is the load shedding, which should not be used, but if you don't have option, you will be using it. Again, continuous, the same one, same thing. Reactive power controllers, its management. The voltage collapse proximity indicators, which are used as an indicator which will tell us how far our system is stable from the voltage collapse point of view. These indicators can be used locally instead of using the global VCPIs. Some sensitivity based indicators can also be used in the microgrids. We use PV and QE curves in a grid, but its analysis at a local point of common couplings can be used for the analysis of the stability. Certain indices, line indices and load indices are also suggested in the literature, which can be used to improve the voltage stability in the microgrid. We should have large number of storage and its efficient use for the improvement of the voltage stability in the microgrid. And there is one important term called reactive power momentum. So there are two things. One is the reactive power and second is the distance over which it is to be transport from one place to another place, transferred. So when we talk about the reactive power transportation from one place to another place and how far it is to be transferred, if we multiply these two things, we can come out with the one new term, that is momentum. And if your momentum is high, you have to reduce it to have the more or very good improved voltage stability of the system. And to calculate this momentum and to use it efficiently, one can use the AI. So this is basically for those participants who wish to do the research in the area of RES or microgrid. The first thing is the planning and forecasting of RES or microgrid with RES. When you have a microgrid and in that microgrid you have a large number of RES, and if you want to use it, then the first point is its planning and forecasting, because forecasting the output of the RES is a challenging one. The planning and dispatch mechanism used nowadays for day ahead market, this mechanism can also be studied and one can suggest some research in that area, some output of his research in this area. Then for conventional, it is very easy to control the generation, but for the RES, it all depends on the weather. So can we have certain forecasting technique or certain planning techniques which we can use such that whatever the generation and forecasting data available, planning or forecasting data available for the conventional one, similarly we can do something for RES. This is basically related with the market operations, so I don't want to go in this one. And then the congestion management with microgrid or with grid or with RES can also be studied, and these are some of the points which we should discuss. But now it is already 9:20, and now I have only 1 or 2 slides with the related to reliability, but I don't want to discuss it now. So in conclusion, we can say that if our grid with a larger integration, the variability can be better handled. If we have a very good forecasting, operation and planning can be done good. If we have very good scheduling, it will indeed give us the accountability of which one is responsible for generation or scheduling. And then with RES mechanism and trading, RE will be an attractive business. So trading and its mechanism is also, these are certain reference. Thank you, and questions.
There are few questions. First of all, let me express my sincere thanks to our beloved Professor Bhavik Sudhar sir for his excellent session delivery. So many dimensions sir has enlightened us where we can do some more work in further research. Sir has covered a lot of topics from control to microgrid topology, how to manage the active reactive powers, all these things sir has covered, even voltage stability, so many things sir has covered in this session, and I hope so all the participants have enjoyed this session and they have got some insights from Sudhar sir session. Now there are few questions in front of me. I would like to ask to Professor Sudhar sir on behalf of our participants. One question. Professor Ravindra Kishan Rao Mankar is asking method for optimal placement of DG into existing system.
So for optimal placement of DG, there are certain optimization techniques available. Using those optimization techniques, one can find out the appropriate location. Now in the optimization techniques, there are two things. One is the objective function. What is the objective function? You want to reduce the cost, you want to reduce the CO2 emission, you want to have more stability. So depending upon which is your objective function, number one, and number two, which method you are going to use. Are you going to use some mathematical models, mathematical methods available, or you are going to use some stochastic techniques or some GA or this kind of techniques? Depending upon that, which method you want to use and which is your objective function. Both these things will decide for placement of DG in the entire power system. These two things. One is the which is your objective function. Accordingly, one see my objective function is X, then I will say that place A is good. If objective function is Y, place B is good. So depending upon the objective function and the method you are using. So I hope I am able to answer that.
Yeah, sir. Wonderful, sir. And I hope so, Professor Ravinder Kishan Rao, you may have got the answer. Now, one more question is from Dr. Sundaram Pandya, GEC Polytechnic Bharuch. He is asking, respected sir, who is the responsible for forecasting of these stochastic models of RERs, wind, solar, etc. Tertiary control or ISO? That means independent system operator.
See, in our country, we have the energy management centers. Normally we call the load dispatch centers. And it's a hierarchy. We have area control system, we have area load dispatch center, then we have a state load dispatch center, we have a national level or regional load dispatch centers. There is a hierarchy. Similar to these load dispatch centers, we have REMS, that is Renewable Energy Management Systems, centers, sorry, REMC. So these Renewable Energy Management Centers basically collects all the data related to the generation of the renewables, and they are much involved in the forecasting or generation of renewable energy sources. Okay, so REMC, Renewable Energy Management Centers. It is only up to national level, but it should also be available at a regional level. Nowadays, the time has come that the REMC should also be there for each state or each control area. Okay?
Yes, sir. Yes, sir. Fine, sir. Thank you for answering, and thank you for answering, sir. Wonderfully, I think so. Professor Pandya has got his queries solved. Also, he is asking, can ISO is directly involved in electricity power pool?
ISO is the independent system operator, and it is doing two types of operations. One is the technical and another one is the market based, economical and technical. And for both the cases, everything will be decided by the ISO, or ISO is basically the dispatch centers. As per the instructions of the dispatch centers, everything should be done.
One more question. We will take only 2-3 questions, not more than that, sir. One more question. Again, Ravinder Kishan Rao Mankar has asked, please suggest references for mathematical modeling of wind turbine, solar PV, small hydro. In the answer of this question, on behalf of sir, I would like to suggest you go through the references. There are many literatures available on the mathematical modeling of wind turbines. Even our research group, including myself, has written many papers in IEEE transactions where wind turbine modeling is given. Even my student who is participant here also, Mr. Sombir, now Dr. Sombir Kundu, he has done a lot of things on solar PV and wind in combination. Even small hydro is done by our group members. That means modeling, control, configurations, everything is covered. And regarding in the above question, what Professor Pandya and Professor Mankar has asked previously, our that means one research student where me and Professor Bhavik Sudhar sir is guiding. She is the participant here also, and she has done a very nice work, and expectedly the paper will be published very soon. And that means that DG placement and all what the question was asked, like DG placement and optimization. That paper you can refer once it is published on the website. So these things are very much available from our research group also, and so many things are available in IEEE transactions. So this is a very relevant question asked, and I hope so you will further search the literatures and you will get some idea from the currently available literatures. So I think so from our side the questions are over, and if I am giving further 1-2 minutes, if any participant, please don't be hesitant to ask questions. Sir is very much cooperative to all of us. He is sitting late, just you can see 9:30. Dinner may be pending. So just you can see the commitments from the experts. You can ask questions if you have. We are sitting here 2-3 minutes more. You can put your questions in the chat box. I will put in front of sir, and definitely you will get your answer, your query solved. Yeah, now I hope so, sir. I would like to invite Professor Divyesh Parmar once again to give the vote of thanks to our respected professor, Dr. Bhavik Suthar, sir. Professor Divyesh.
Yes, sir. Am I audible?
Yes,
Yeah, you are audible.
Sir, it is an immense pleasure for me to express gratitude to respected Professor Dr. Bhavik Suthar, sir, under whose headship I have had the privilege of working. He is truly a dynamic personality. On behalf of this FDP team, sir, and the institution and all the participants, I extend our deepest thanks for the exceptional lecture you delivered during this FDP. Your insightful exploration of topics such as grid evolution, renewable energy sources in India, the microgrids with the renewable energy sources, especially operating challenges, control and stability, was not only enlightening but also thought-provoking. I trust that the clarity and the practicability of your presentation resonated deeply with all the participants, making the session both highly educational and engaging. We sincerely appreciate the time and effort you dedicated to addressing participants' queries and fostering an enriching learning environment. I hope your lecture continues to inspire all participants to explore this dynamic field further. Once again, thank you so much, sir. Thank you very much.
Sir, thank you very much on behalf of our entire organizing team, our principal, sir, our respected head of department, Professor Doshi, sir, our co-coordinator, Professor Divyesh Parmar. Entire organizing team is very much thankful to your time and whatever the expertise you have made available to all the participants, sir. On behalf of all participants, I am extending my sincere thanks to you, sir, and hopefully we will be continuing our associate working together, and in future something good will happen. Thank you very much, sir. Thanks a lot.
Thank you. Actually, I should thank you all because you have given me the opportunity to interact with these participants, to you. And, I was, of course, it's a dinner time, but I will take only 1 or 2 minutes. I was, since last 3 years, I was in charge principal and I was unable to do this academic or technical work. But you had given me this boost, so again I will start doing these technical and academic activities now onwards with more enthusiasm. Last 3 years I have wasted. I think I have wasted in principalship.
But sir, that is also important for our system. The people like you, if you are, that means if you are working from that capacity, definitely system is going to get the advantage from that place also, sir. And we wish you all the best for your time ahead, sir. Thank you very much.
Thank you.
To join us, sir. Thank you. Namaskar, sir. Good night. Good night.
Good night.
All the best, sir. Thank you, sir. Thanks from my bottom of heart. Thank you very much.
Thank you.
Okay. Yeah, thank you participants for joining till 30 minutes extended session. And I hope so you all are enjoying the sessions. We are trying to get out of maximum. And thank you for your cooperation. You people are cooperating so much. More than 100 people always join throughout the session, whatever we are observing from here. Thank you, dear participants. Thanks for your cooperation. Without your cooperation, sessions cannot be made interactive. People are asking questions also. All the sessions are very much interactive. And thanks a lot for your all cooperation provided throughout the these 4 sessions which we conducted. Thank you. Next session we will start tomorrow sharp at 6 p.m. My request, though you all are sincere, it is observed from here, but once again, my personal request, entire organizing team is requesting to all of you, you keep joining at right time, and please continue to join throughout the sessions. Thank you very much. Good night to all of you. Thank you. Now you can leave. Thank you.